guess I'll hold the microphone. The way you advance is with advance.
Use this.
Well, that'd be great. Hi, everyone. Good morning. Certainly are in. That's okay. There's some seriously technical. And a piece of tape. Most of you people I know. And I'm going to want to stand back here. This computer's going to want to restart here. No, we don't want that to happen. So, the guys have put together these wonderful graphs and equations and the like, and I figured I'd tell you a story this morning rather than a lot of that. But what we're working with is cold asphalt recycling, and let's see, we'll get right into it. What is it? This is a mill. This is a lime tank and a mill. And so what we're going to do is we're going to take up a piece of pavement, and we're going to reprocess that pavement, and we're going to reprocess it in there's the mill, there's the processing unit. We're going to crush the oversized material. We're going to place it in a pug mill. We're going to add some emulsion. In this particular case, we're going to use an emulsion that has no solvent in it. And the reason for that is that in the state of Utah, at this juncture, it is illegal to use a material with a solvent in it due to the VOCs. So we're using a material that has less than 1% volatiles. We pave that, we spread that out on the ground in the thickness of the lofted material, and we compact it and make a road. This particular pavement was capped with 3 inches of asphalt. Made a really great project. This is US 491 Monticello to I don't know, the Colorado border. Sometimes when the pavement is variable, when the distances are short, when space is confined, it's better to work with a centralized plant, which is what we take the whole recycling train and put it in a yard and dump the milled asphalt into it. You get the advantages in that case of stockpile management, and you increase your control over the product. Short trucking distances can be obtained in this manner, and you're processing a milled material, a mined material, directly back to the road. So why cold? Because you're mining the road for the materials to build the road, so you're saving on trucking and you're reducing your carbon footprint. But it costs you 35 to 25% less than if you had milled it and filled it. You also get the structural advantage of the recycled material. You're putting back nearly the original structure. Even if you cap it, you retain that original structural value. And the material actually has a reasonable performance. It is not HMA. But it has held up. It has proven, if done correctly, to hold up very, very well, perform very well. Let's see, this one, not this one. So there is another photograph of SR 491. You see the longitudinal joint crack in it, but otherwise the material has held very well. This is now a 10-year-old pavement. But sometimes we have some troubles. 7 of our projects in the last 10 years have succeeded, and 4 of them have presented problems of this nature. And the problem that we had 5 years ago or 4 years ago when we started this project was, why does this one do this and why does the other one do that? We can't tolerate a 30% failure in our projects. We don't do it if we suffer this at a high rate. So why the failures is the subject of this. Going into this, we have a specification that is written for and by a particular company who has expertise, and as the system becomes commoditized, that specification no longer is adequate to control a project. What are the key values? What are the key issues? How do we properly control a project? So one of the questions really is, why do some emulsions break properly and other emulsions do not break properly? How do you anticipate when a cold recycled pavement is ready to release to traffic? Typically, we'd go out and we'd run the truck up and down the road and turn the wheel and see if it would ravel. We don't know really anything about the train, the process that we use to get this thing placed early on in this. We're really blind to these issues. So what did we find? Well, like hot asphalt, a cold recycle stabilizes due to an increase in viscosity. In hot mix asphalt, that is a cooling issue. In emulsion, that is a breaking issue. So how do we understand how the emulsion interacts with the particles that it comes in contact with, and how does it break? And what is the difference between this chemistry and this chemistry and this chemistry in terms of that performance? Big question. We also learned that the asphalt particle in a cold recycle is a rock. It's a black rock. And with temperature, that rock changes in shape. With temperature and compaction, that rock is a amorphous particle. You look very, very concerned back there, John. it is a very, very, very concerning issue because it means that the void space in the mix design changes with temperature. That means that the space in which you put the mortar changes with temperature. Something that was never considered in the original design processes. As with other HMA, as with other paving materials, if you control the voids, you control the performance. And the best performance occurs around 6 to 7% air voids. The relationship between the large aggregate void spaces and the mastic portion of the mix is a moving target and has to be accommodated in the production of the material. You must recognize what the VCA is, the voids in the course. I'm going to use a new word here, the voids in the course wrap, VCR, is a moving target, and therefore the mortar fraction of the mix is a moving target, and therefore the binder content is a moving target, and therefore the lime content is a moving target. How do you manage that in the field? Really big question. And then we learned that the best emulsions delay their break for a period of time while the workability issue is in play, and then they must gain rapidly in viscosity. They must break and break hard to get you back to a traffic, release to traffic arena. So we're going to talk about these issues in more depth, but over the past 4 years, these are the things that we have learned and have presented to this conference. This is all known to this conference at this point. We now have applied some new technology, semicircular bending test, fracture energy test has been incorporated in place of the compact geometry tinsel test, which was a test for fracture energy in the original design. Very difficult test to run. This is an easier way of getting at this piece of information. Of course, we are trying to figure out how to now take the standard mix design technology and apply it to these mixes. Big question, how can you get away with 2.5% emulsion and get high values of fracture energy? We'll explain that. One of the big arguments in the field has been you get to deal with, the mill produces what the mill produces, and you have no control over it, and you just have to live with it. And we've dispelled that argument, and we know a lot more about how to control the gradation. One of the really interesting findings was that we always thought that emulsion was driven by its chemistry. The break in the emulsion was driven by the chemistry of the emulsion. Isn't true. The break of the emulsion is driven by particle size and the moisture content and the temperature. And that paradigm shift has created a whole new way of looking at this problem. And the last thing is that we now understand why we put lime in the mix. So there's a SCB, and What we found is, let's see, an SCB requirement is minus 0.6. That's, I'd put an equation up here, but you guys would get lost and there's no point in it. 0.6. Higher is better, lower is worse. Tested Monticello at 0.82. Very, very good number for a CIR and better than most HMAs. So we know that the fracture properties of the material can be built with a very high fracture energy. We know that the properties of the material, it can be built with a very good rutting value. We know that if we get a 0.33, which is what we got on Strawberry US 40, we get failures. And so we are very suspicious that the failure that we got down on Black Ridge, which is a picture I showed you earlier, would have had a very low energy value. So along with proper binder content and good particle distribution, you can obtain good mixed design practices. You can obtain very high fracture resistance, as good or better than hot mix asphalt. Fracture energy has always been used in the mixed design. This test procedure is a much easier way of doing it, but this can't be used for field purposes because these things have to cure and they have to gain strength before you can properly test them. You got to have a standard and a temperature and a moisture content that you get these samples prepared for the laboratory. Lots and lots and lots of repetition to get to those conclusions. I figured that I'd tell you a story. So don't mind my cartoons, but this is basic mix design. You have a volume of material. It's filled up with your coarse fraction. It's filled up with your fine fraction. It's filled up with your asphalt binder. It's filled up with some air. You set the air. You want to have enough room for the emulsion to exhaust its water. So you have to have room for that to happen or you're bleeding all over the place. You have to have enough water to liquefy, we'll talk about that later, the fine wrap so that the emulsion doesn't break in it. You have to have enough room in the coarse wrap to fill the area with fine wrap, 5 minutes. With temperature, this goes down, this goes up. That stays pretty much the same. That stays the same. You can predict, based on temperature, based on our findings, how that's going to work. And you can calculate and adjust for those issues and dynamically adjust in the field. Of course, we want to know how it is that you can get away with 2%, 2.5% emulsion or 1.63%, 1.6% asphalt when a standard asphalt mix takes up 5% binder. And the way you do it is that all of the small particles in the mix are bound in asphalt already. And so the particle sizes are bigger, and what you get out of 2.5% emulsion is 4 microns of film thickness in a standard film thickness calculation, and voila, you have the standard HMA film thickness, and you get the same fracture energy results as an HMA. It's rather an interesting calculation. So we want to talk about why emulsions break, and they break because you increase the pH too much. They increase because there's too much fine particle. They break because there isn't enough moisture to cover the fine particles in the mix. They break based on emulsifier concentration. And sometimes they break because you vibrate them when you roll them. I'm sorry for this picture, but we were talking about liquefaction, and I wanted to let you know what liquefaction looks like. And this is probably still on the vibrator, but you see this shine come to the surface. That's when the pores are full of water and there's no more room, and now you can put emulsion into this mixture, and the particles are not dry enough to break the emulsion. Since 90% of all of the action in the system, all of this chemistry and all of this liquid and all of this occurs in the small fraction of the mix, you measure the small fraction of the mix and you have the properties of the total mix. So we went to a demulsifying test for the emulsions, and this cone penetration test. It's done with a cone penetrometer and a Dixie cup and a TNT machine. And what we get is a dormant period and rapid increase in break. There are a variety of conditions that have to be met to create that. The system has to be in a dry environment where you're getting evaporation. It has to be in a warm environment where you're getting evaporation. It has to have specific particle size distributions and some other things that create that kind of test. We're still working on some of this repeatability based on particle size distribution and the type of particles that we're using. I guess I went through that. So quicklime, we use quicklime in the system, and we were wondering why, because there's so much water associated with it that we overwater that untreated base course, and we can't compact it because everything is full of water. So why are we using quicklime? Why are we adding all this water? Why are we adding this to the system? It certainly isn't a break issue. The pH that it creates isn't high enough to break the emulsion. The amount of water retards the break of the emulsion. We want to be able to do a better job of controlling that water. And so what we learned was that historically they put the lime in the system because it creates heat. And if you slake the lime first, you lose all the heat. And so our process has always been to slake the lime and then put the hydrate into the system. But the early task was to use the heat of hydration to increase temperature so that you could drive the emulsion to a break. So with modern solvents, you have no longer a reason to use lime in the mix. And so unless you need it for stripping, we're recommending not to do it. This is Tooele, Ophir Canyon. That's our latest foray into this. This was a fixed plant project where new materials were brought in from a milling project, stockpiled. And the interesting thing about this is in the cure, usually you find that this whole surface will be bleeding, it will be running water. And there was enough void in this mix to take the water that we put into it and the water that the emulsion drove, and what we had was a moist material that set in 3 hours and was ready to put traffic back on. Very, very good demonstration of the new things that we've learned about CIR and the usefulness and the repeatability of this tool. Questions? Yes, sir.
You said you had 4 projects that were sort of
No, they failed.
okay, failed projects.
Black Rock was a disaster. Black Ridge was a disaster on I-15. US 10, there were 2 projects under the trucks we were talking about earlier. That coal road, we squashed it. It was a mess. There were 4 of them that strawberry on US 40, massive failure.
How many were the recycle train versus sort of in place? Were you
They were all recycle train.
They were all on train? Okay. How about the others that did less?
They were all, so this is the first time we've done a fixed.
Well, that's the first time you actually sat in one place.
This is the first time we've done a fixed.
So we don't really have a handle yet on how much better it is.
It's a matter of feedback to the train. It's a matter of rapidly feeding back information to the train and adjusting the trains. The natural thing happens. As the day warms, the train goes faster. As the train goes faster, the material gets coarser, less fines, more. But as the day warms, the coarse aggregates collapse under the roller. So the thing is automatically compensating for the change in conditions. And if you manage that correctly, you are much more likely to get success. The problems with some of these is we try to do them cold and in the rain, and that's not a good idea. And some of the other problems we've had have been, we didn't use the right emulsion. Anything else? Thank you.
So I'd like to thank you for being here, and thanks again to our presenters.